For the introduction. So yeah, it's my pleasure to visit YITP as always, and then thank you for this opportunity to introduce our recent result. So yeah, today I'm going to talk about something called higher center charges, and then if you never heard of them, no brainer. It's relatively new quantities, and then it was somewhat first introduced in the, I think, math literature, but we found some useful way to use them to understand many body quantum systems in 2 dimensions, in particular for those states which have topological order. So I will first introduce the concept of topologically ordered states, which may be familiar to most of the condensed matter physicists, but I see a mixed audience here. So I will introduce some basic properties of topologically ordered phases of matter. And then I will make a contact with the higher center charges. And then our contribution is to find a very explicit way of extracting or calculating this quantity higher center charge from some operations, partial operations. So that is going to be the outline of my talk. And so this will be followed by a demonstration using numerical method. But before going to the details, I first want to acknowledge my collaborators. So Ryohei, he's now postdoc at the University of Maryland. He's my long-standing collaborator. And the Taigei is a graduate student at UC Berkeley. And then Tomo is another graduate student at UC Berkeley. They both a member of group of Mike Zarato. And then Roger Mon is another older friend of mine. We collaborated on various subjects. Okay. So let me start with topological phases of matter in general. So basically, these are the kind of interesting or exotic states of condensed matter, which are not characterized by symmetry breaking paradigm, at least in a naive way. So there's no other parameter to talk about. So conventional way to detect and distinguish different phases is to use local correlation functions or maybe other parameters. But topological phases are kind of distinct in that they escape this paradigm. Okay. By now, I think there are many interesting known examples, and the most famous is this quantum Hall effect. There's also integer and the fractional quantum Hall effect. But as a start, I'm just presenting integer quantum Hall effect. So you can think about a phase diagram in terms of the magnetic field, and then for each phase we plot transport quantity sigma xy, or in this plot it's actually rho xy. But anyway, for each plateau, we realize particular gapped phases of matter. But these phases are not distinct from the point of view of the symmetry. But they are characterized by some topological quantities. In this case, it's quantized Hall conductance. So we see this famous quantized Hall conductance. And then there are many other examples. For example, you may have heard about topological insulators or superconductors, or topological state in spin systems such as Haldane spin chain, and so on and so forth. Typically, topological states are. I started by saying that topological states are not characterized by local order parameters, but instead they are characterized by, for example, some topological quantities, like this Hall conductance for the case of quantum Hall effect, or maybe some other properties, such as the existence of exotic excitations. So these are the, in particular, topologically ordered states are such examples. So these are the phases which are characterized by the existence of exotic excitations, which are called anyons. So the very existence of these excitations are like order parameters in some sense. And then the different topological states, different topologically ordered states, are characterized by the different set of anyons. Okay, so what are anyons? So usually, if you exchange a quantum particles, I have a picture here. So as you exchange quantum particles, like we see along these trajectories, quantum wave functions typically pick up either plus or minus sign, depending on the type of fundamental particles you have. But anyons are neither boson nor fermions. Okay. So for example, as you exchange two anyons, instead of plus minus one, you could pick up some phase, which is more interesting, like e to I theta. Or even more exotically, as you exchange the location of these two anyons, you may get a different state or superposition of a different state. This is somewhat more simpler version where we say we have a billion anyons. On the other hand, if you have a this type of a more exotic exchange statistics where not just a phase, but we actually get a different state, we say we have a non-abelian statistics. Condensed matter physicists over years worked on this type of exotic phases or exotic states which support anyonic excitations. And then we basically say these states which support anyonic anyonic excitations, they have a topological order. So this is the concept of topological order. The canonical example for the topological order is the fractional quantum Hall effect. I presented integer quantum Hall effect, but now I'm talking about quantum Hall effect, which are realized at the fractional filling of electron numbers. Okay, so we realize more exotic state, which are fractional quantum Hall states. Okay, I listed two more examples. I think this is the candidate of quantum spin liquid, which has the which is basically underlying degrees of freedom are like interacting spins, but instead of having a symmetry breaking ground state, people speculated. This case is more controversial than the fractional quantum Hall effect, but for this type of materials, quantum materials, people speculated the existence of quantum spin liquid ground state. And then yet another example I have here is a more artificial or synthetic systems where we have a artificially arranged neutral atoms in this pattern of Kagome lattice. And then people recently realized that the quantum spin liquid in this type of engineered systems. Okay, anyway, the list of topologically ordered experimental systems are being growing. And then, so that's kind of very interesting from the fundamental point of view, because these are the states which we usually don't have in the solid state, but we could have now have a more interesting quantum ground state. I should also say that there's the idea of using non-abelian statistics to do stable quantum computations. That's another kind of interest from the practical side, to look for and realize such topologically ordered states. Okay. So I already mentioned basic properties of anyons. Basically, they don't obey bosonic or fermionic exchange statistics. But to go on, I have to present a little bit more details about how we characterize anyons. So here's the perhaps more things I should say, but for my talk, these are the quantities I'm going to need. So okay, so this is how we describe anyons. Okay, basically. So we first want to have a list of all anyons I have in a given topological phase, because we could have a multiple types of anyons for a given phase. So we first make a list of possible anyonic excitations for a given topologically ordered ground state. So I just use A to label different kinds of anyons. For different kind of topological order, this set of labels A are different. Here I just have two examples. So Z2 topological order is a kind of one of the simplest kind of topological order. In the previous example, this artificial Rydberg atom system, this is considered to be realizing Z2 topological order. Z2 topological order are characterized by the existence of 4 kinds of anyons, one, and then electric anyons, magnetic anyons, and F is a composite. One is a trivial excitations, which is just kind of included for completeness. But anyway, one just means this is not anyonic, but it's just included in the list. Okay. And then more interesting topological order is the so-called Ising topological order. I will present some specific theoretical model which may realize this Ising topological order. So Ising topological order is characterized by 3 anyons, 1 and psi and sigma. And then maybe this symbol doesn't mean anything for now, but sigma is a non-abelian anyons. And then as I said earlier, this is perhaps not the best example, but it can be realized in this Kita spin liquid, or particular phase of this Kita spin liquid, or some complicated fractional quantum Fourier effect that may host this type of potentially host this type of Ising topological order, which has no abelian anyons. Okay. Now, okay, so this is just a way to label anyons, but now we have a basically 3 quantities: D, theta, and S. So these are important quantities. So the first quantities, this D is associated to H anyons, and these numbers are called quantum dimensions. So this basically measures non-abelianness of given anyons. So as I said, anyons can be either abelian or non-abelian. Being non-abelian means for a given location of anyons, I have a multiple state. So you can think about the dimension of space, the space spanned by these non-trivial states. So basically, this D is kind of measuring the Hilbert space dimension of anyons for the fixed position of these anyons. Okay. Other 2 are more related to statistics. So theta is related to like a self-statistics of anyons, or what we may call it spin. So as we twist the world line of anyons, so this picture is supposed to describe the world line of anyons, just like I have a picture here. So you can associate some sort of numbers for each trajectory of anyons. So this is the trajectory associated to a single anyonic line, but it's twisted. Okay, so that somehow encodes the self-statistics or spin of anyons. So that's, we call it topological spin, or we call it T. So I may use either theta or H, but let's say we have this set of numbers associated to each one. Another interesting quantity is this quantity S. That involves word line of two anyons, A and B. But if you follow the trajectory of these anyons, they are kind of exchanging positions. So this is associated to the exchange, or we call it braiding in this terminology, but it's associated to the braiding of anyons somehow. So these are the kind of quantitative way of describing properties of anyons. So we are interested in, like we measure all the parameter. If you are somehow confident that you are obtaining a topologically ordered state, you may be interested in knowing all these numbers. Okay. The final quantity I want to introduce here is something called central charge. So you may remember in my title, I have a higher central charge. But before talking about higher central charge, I just want to say something about central charge. So central charge is associated to the transport of the edge state. So another important properties of the topological state is that topological states support edge excitations if you make a boundary to the system. So then you can ask how much heat transport I have at the boundary of a topological system, and this number C is related to the thermal transport along the edge in unit of this. Okay, so that's the concept of a chiral central charge. And then, somewhat interestingly, chiral central charge and the other properties, other data I introduced earlier, they are related by this magic formula, where exponentiated central charge with 2 pi and 1/8, it's related to the sum of all anyons with this quantity. Okay. So yeah, today we want to somewhat generalize this formula to something called higher central charges. Okay. But before doing this, here's some basic questions. So if we want to study topologically ordered state, there's some questions such as, do we know all data to describe topological liquid? I didn't list all data, but I just listed representative data. And then one could also ask, in addition to data known in the literature, maybe we may have some more data which we don't know yet, and so on and so forth. So there's kind of a quest for looking for interesting topological data or topological response for topological state in general. But today I don't follow that path. I will just focus on the quantities which we already know. D, theta, and the S and C, they known to exist. But the question I want to ask today is that how do we really measure these quantities? Since I'm a theorist, I don't really mean measure, unfortunately. So that's why I put quotation mark. But these quantities I somehow abstractly introduced before. How do we actually calculate? If you somebody hand unknown, wave function, ground state wave function to you, or maybe you get it from some computer simulations, how do we get these numbers, d, theta, S, and so on and so forth? That's the kind of question I want to ask today. So in a slightly more general context, there's the huge effort of measuring topological data in general. For example, I casually said that fractional quantum Hall effect realizes anionic excitations, but to actually establish the existence of anionic excitation, it's a huge experimental effort. And it is actually only very recently that people measured abelian braiding statistics in these experiments. So that's relatively recent. Fractional charge, for example, has been measured much earlier, but braiding statistics, when it comes to the down-to-earth experimental measurement, it's only very recent. Okay. Another quantity which I didn't mention much in this talk, but there's something also called topological entanglement entropy. So that's a kind of universal part of entanglement entropy, which may capture the topological property of topological liquid. In particular, from the entanglement entropy, you can extract this number D, which is the sum of, I introduced quantum dimension, but this is something called total quantum dimensions, which you basically sum of quantum dimensions. So this has been a useful smoking gun to establish the existence of topological order. And for example, in recent quantum computer study, so people realized a topological state in quantum computer, and then they verified the existence of topological order by actually measuring, or measuring in quotation mark, actually computing entanglement entropy. And then we can sort of see that topological order is sort of there in your quantum computer. Okay, but this quantity is only know the sum. It's a total quantum dimension. It doesn't have a resolution for each particular anion, and also it doesn't know about theta. So topological entanglement entropy has been around for a long time already, but there's some topological states which we can't distinguish just by using topological entanglement entropy. So we may be interested in finding more probes for topological system. For example, Z2 topological order and then Ising topological order are introduced. They share the same quantum dimension, so you can't know which state you realized. Okay, so we may need more probe. Then I should also add that central charge has been accurately measured also only very recently for fractional quantum Hall state. So there's a I just mentioned that the extracting universal data either in experiment or in computer simulations or in quantum computers, it's being already a challenge. Okay, so I want to follow this type of thinking, and then today I want to propose to do something slightly different from, let's say, topological entanglement entropy. So I don't know the format of the meeting, but by the way, if you have questions, please just interrupt. Okay, so today I would propose to study something we call partial rotation. So it is defined as follows. First, I consider two-dimensional system, and then for convenience, I just consider infinite cylinder. This just for theoretical convenience. So I have some quantum state supported on a two-dimensional cylinder. And then I may be interested in what kind of topological order I have, and then what kind of anions I could have in this topological phase, and so on and so forth. So to learn about anionic excitations, I would do the following. So I consider rotation operations. So I consider to rotate location of all particles along the circumference. Okay, so I rotate my state just by angle theta. So that's operation T theta. I put this sub index A here because I do it only for a part of this infinite cylinder. Let's say the half of the cylinder. So I first consider to bipartite my cylinder into two regions, and then I do this rotation only for region A. Okay, so that's how that's why we call this operation partial rotation. Okay, so the idea is that to do something, something to your ground state wave functions, which is not truly local, but somewhat non-local, because we already know that topological state cannot be studied just by using local correlation functions. We do something global in the sense that this is the operation which is not localized on the point, but it is for the entire sub-region A. And then by studying such operations, we may be able to learn more about the properties of topological ground state. Okay, And then we just consider the expectation value of this partial rotation operations. And then I get some number, which is this calligraphic T. And by the way, since it's a topological system, I could have something called topological ground state degeneracy, which is a ground state degeneracy not associated to symmetry breaking, but it's a type of degeneracy we could have for topological systems. So anticipating this, I label my state with this subscript A. So I could have multiple ground states. So I do this calculation for each ground state. Okay, so this is the definition of this calligraphic T. We were not the very first to study this type of quantity. For example, in the past, this was used in this paper to extract the chiral central charge, regular central charge, and also topological spin. But today I will do something slightly different. And then it's really motivated by my older paper with Ken. But at this time, 2017, the concept of higher central charge officially did not exist. So we did something already in this 2017 paper, but we're kind of revisiting the idea of using partial rotation to study topologically ordered system. Okay. Space cut.
What happens with orbital? Because space is typically difficult, right?
Yeah. So that's a good question. So there's some details in our paper, depending on how you cut. My quick comment is that it may affect more this momentum polarization part because its entanglement spectrum is not the CFT spectrum if you do the orbital cut. But in the higher central charge calculations, I may suspect yeah, short answer is I don't know. We still have to either real space or the orbital cut. We still have to cut at the right position because you have a multiple unit cell if you have a fractional state. Beyond that, it may not affect so much, but we didn't make a very serious comparison. Yeah, we can perhaps talk more about this.
Yeah, but like presumably in your numerical study, it has to be an orbital cut, right? Because in the MRG, it's just not. It's like not possible to do space cut, it seems.
Yeah, so we do. Yeah, so that's right. So we do basically tensor network bond cut. Yeah. Yeah. Right. Okay. So I hope I introduced the setup. So now I want to introduce formula, and we will verify this formula in various examples. So this expectation value, we look at this expectation value at discrete finite rotation angles. And then in the limit of large circumference, this is the formula we got. This is sort of already presented here, but we did more general calculation in this paper. And then this is the this part is as it turns out, it is related to something called higher central charge, which I will introduce in the next slide. And then this is for the case where we have a trivial ground state. This label A is the trivial anion, but we could also do the similar calculation for more generic topologically degenerate ground state. And then we get somewhat similar formula, but we now have a dependence on the modular S matrix. Okay. I will first explain this part, and then I will perhaps briefly mention the derivation, although perhaps I don't spend much time there. And then I will also demonstrate the DMRG calculation. Okay, so this part turns out to be related to something called higher central charge, which was introduced in this mass literature. I read this paper briefly, honestly, not in the great detail, but I think these papers are more like purely mathematical motivations. But later people found this quantity turned out to be useful. Okay, but maybe first comment is that this looks like the so if you remember the relation between central charge and d and theta, we basically change powers here. So I think that's the motivation to call this quantity a higher central charge. So we have additional power here. Yeah, so this was introduced in this paper, but kind of interesting physical application was really stated in this paper, in physics paper. So this quantity may be useful. It is useful to say something about the properties of the edge state. So like I said earlier, if you have a topological system, you could support the edge state, and then, for example, you could have a thermal transport around the edge. But this quantity says something, some details of the edge state. Okay, so in particular, this quantity is useful to discuss the gapability of edge state. Okay, so what is gapability? So if you have edge state, in the simplest case, you could have just the let's say propagating degrees of freedom to the left. You could have just purely chiral state. In that case, okay, in condensed matter terminology, there's no backscattering you can induce. So in such case, you cannot gap your edge state. Okay. So in this case, you can simply, because the thermal transport is related to the chirally propagating edge state, non-vanishing thermal conductivity is already tells you that the ingapability of the edge state. Okay, but you could consider more complicated topological states with multiple edge state. Okay, so for example, you could have a boundary which supports both left and right moving boundary mode, and then you could have a situation where thermal conductivity or chiral central charge is actually 0. Okay, in this case, because you can allow a interaction between these two edge states, you can potentially open a gap on the boundary. Okay. But depending on but story does not end there. Depending on the property of the actual edge, you could or you could not gap out this edge. Okay, so that's a concept of gapability. For example, you could have a this is maybe the kind of nomenclature, but you could consider edge of the nu equal 1/2 edge. And you could also have the nu equal -1/4 edge, which is the counter propagating. So at that level, just by looking at the direction of these propagating modes, you may think that we can gap out the edge state. But as it turns out, sometimes you cannot. Okay. So the question is, can we have a criterion for the gapability of edge state? So then. As it turns out, these higher central charges are useful in the sense that, at least for the Abelian topological order, topological states which only support Abelian anyons, using higher central charges, you can write down the criterion for necessary and sufficient condition for the gapability of the edges. Okay. So that's the kind of interesting application of this higher central charge.
So is there an example of a fermion topological insulator where it's ungappable?
Free fermion topological insulator. Yeah, it's gappable. 1, 0, 1, 0, 0, minus 1.
So if it's free, it's always gappable.
Yeah, free. In that case, you need some symmetry. Yeah, here we are not imposing symmetry. Yeah. Yeah, clearly this is the interacting case. Other questions? Okay, so so that's the kind of interesting in higher central charge. But question is, how do we extract this number? So the central charge, as we already said, you can extract it from the thermal transport, or if you know the DC d and theta, you can combine d and theta to get some information on the Carter central charge.
Is that the same central charge you can get by looking at the entanglement entropy and then doing finite size scaling?
Sorry, which entropy is it?
So the formula goes something like the logarithm of the system size.
Yeah.
This gives you like some linear behavior, and the slope of that curve is the central charge.
Sorry, logarithm of this quantity or logarithm of
So you just look at the central cut and like some RT system.
Yeah. So you can get central charge that way. You can get the central charge from the entanglement spectrum. Yeah, that's not the problem. Yeah, that is not the problem. Yeah. Yeah, here we are interested in higher central charge.
And there it's not possible to get it via finite size scaling.
I think you're talking about in 1D. I think this is in 2D. Are you talking about the 0-3 business?
Yeah.
Oh, 1D. No, this is 2D. Sorry, this is 2D. This is 2D. This is a 1D edge of 2D, and the entanglement spectrum in 1D. Yeah, but the question is, if I know the entanglement spectrum, can we still get this just from the entanglement? Maybe because the if I know the entanglement spectrum, but I still need to know the angular momentum eigenvalue for each state or something like that. But that's basically how we get this result. Yeah. So yeah, it's closely related to the full knowledge of entanglement spectrum. Okay. Other questions? Yeah. This is only for abelian case. So you said d equal 1, and then so then in this case, yeah, maybe I'm missing some factor, but in this case, sum over theta gives you c minus, and that's what I'm saying. So if if n is 1 and d is 1, yeah, this is the formula I presented before. That's all I'm saying. Yeah. How can we prove this? That's, I think, kind of something. Okay, so I don't know what is the best way to derive it, but yeah, for example, if I don't know this is the best way, but you assume the properties of anion fusion and the S, fusion and then other consistency conditions, and then you manipulate this consistency condition pentagon or whatever, and then eventually you can prove this formula. Yeah, it sounds like a magic. It's a non-trivial constraint on the topological data. You cannot give arbitrary DC, and S, to say you have a consistent topological order. Yeah. Okay, so questions? Okay, so for the interest of time, I will just move on. And for example, I introduced the Ising topological order, and then I listed, this is an example of higher central charges up to 2, 3, up to 4, I think. Yeah, 1 up to 4. And this is another topological order, U1 level 2, which I will introduce later in the context of fractional quantum Hall effect. Okay, but once again, how do we extract or measure a high central charge? And then that's how we got interested in the partial rotation operations. And then we proved this formula analytically. So the quick note on the derivation. So derivation is basically that it is as follows. So since I'm only interested in the operation TA acts only within region A, so that means I need to know I don't have to know the whole state. I only need to know the reduced density matrix supported on region A. So basically, I need to know the entanglement spectrum for the reduced density matrix region A. But by bulk boundary correspondence, or maybe I forgot to cite some papers here, but by something called Lee-Haldane conjecture, the spectrum of reduced density matrix is given by the edge state of physical edge state of topological system. So by using the knowledge of the reduced density matrix, we can just go ahead and compute this quantity. More expanded version of the explanation is here, which is perhaps I don't need much, but this is what I'm saying. So the entanglement spectrum associated to region A, I can basically read it off from the property of the physical edge state, which is described by some conformal field theory. But from that assumption, we can compute reduced density matrix explicitly. Or sorry, reduced density matrix is this physical edge Hamiltonian, and then from that knowledge we can just calculate the expectation value of partial rotation operator. This type of calculation was done first, as far as I know, first in this paper, which I perhaps mentioned before. But in this older paper, people were interested in the small rotation. And then this goes by as a momentum polarization. So for small angle, expectation value behaves in this way by using the method dimension. So it will capture regular chiral center charge, and then if I consider some topological ground state, it also captures the spin of anion, and there's some another interesting part which is related to Hall viscosity, but I won't mention this for the interest of time now. What we found is that the calculation for small theta and large finite theta is somewhat different, and for large theta, we had to do the separate calculation. Then this is the slide which tries to explain that distinction. And then this slide doesn't do a very good job, so you can safely ignore almost all these formula, unfortunately. But basically, depending on this n. So remember, I'm considering the theta, which is 2 pi divided by n. Okay, so but there are two regimes, and then in this regime, n is in this regime, n is very large. So that means rotation angle is very small. So then we just get momentum polarization calculation. But if n is small, we have to do separate calculation, and then there's two regimes. Okay. So I just wanted to sketch some analytical ideas here, but if there's no question, I will just move on to numerical evaluation of higher central charge and try to compare with the analytical formula which I just presented.
What's the example of that?
Yeah, I know what you mean. So yeah, so I think if you fix this L measured in the unit of correlation, so L is a circumference, then it's a crossover, obviously. But if you take the limit of 2D limit where circumference goes to very large, I think then these two regimes are sharply distinct. Yeah. So yeah. So that we also see in the DMRG calculation. You have to make it very large to converge to this result. Yeah. No, we are always in the. Is that right? No. Yeah. So if you make yeah. Okay. So Yeah, so if you so maybe let me put this way. If you fix L, like the circumference is 40 in the unit of magnetic length, you cannot make very large. You cannot make very large n to extract higher center, super higher center charge. But first few, psi 1, 2, 3, 4 may be fine, but eventually you see a difficulty. So then you are in the regime. You kind of cross over to the regime, which may be more in this region. Okay, other questions?
Well, what is the relationship between higher central charge and this partial
Yeah,
rotation?
so that's right. So so yeah, we basically if you know the chiral center charge, we take so numerically we get either this or this. Let's say this.
Okay.
And then we just factor out this part. Let's say we do separate calculation that you can do, for example, just by doing momentum polarization calculation. Then you factor out this, and then you look at the phase of this part. That is the higher center charge.
I see. So one means ground state.
Oh, sorry. One means ground state. Sorry,
with
I mean trivial ground state.
trivial ground state. I see. In the CFT calculation, how to implement trivial or non-trivial ground state information in the CFT calculation? How to implement it?
That's in CFT calculation. Since you know the detail, I just give a technical answer. You just pick a particular Ishibashi state.
I see.
Yeah.
Okay.
Okay. So this my time is running up. I just want to finish with numerical results. So first we looked at this something called Kitaev honeycomb model. Remember I presented alpha ruthenium chloride, which is a candidate for Kitaev spin liquid, but this is kind of cleaner version or a theoretical version of this magnetic spin system I introduced. But anyway, it has actually started with this famous paper by Kitaev, where he wrote down this model. It's a two-dimensional quantum spin model, which is exactly solvable. And then it is a honeycomb lattice model, and then interaction depends on the direction of the bond. Okay, X means sigma X, Y means sigma Y, Z means sigma. And then we add these three spin term. So I think I have a very small but some finite three spin interaction. And then if you look at the phase diagram of this model, it realizes two topological order. One is the toric code or Z2 spin liquid or Z2 topological order in this shaded region. But near the center of the phase diagram, I have a non-abelian phase, which is the Ising topological order. Okay, so this has been around for many years already. But we first use this model, and then this model doesn't require DMRG because it's exactly solvable. We have to do some numerics anyway, but anyway, this is not DMRG calculation, but we can compute the expectation value of partial rotation. And then as you make this circumference large, the phase of this partial rotation saturate, like a 0.7, 0.2, and so on and so forth. And if you compare this with the theory prediction, which is listed here, that's basically what we see here. Okay, so yeah, I mean, maybe strictly speaking, our derivation depended on the assumption that spectrum entanglement spectrum is given by the perfect CFA spectrum. But in the lattice model, this is not entirely true, but nevertheless, theory prediction and the numerics agree rather well. So this is for the Ising phase. We could also look at the Z2 phase or toric code phase. And then I didn't say this, but in the Z2 topological order phase, the higher central charges are all trivial, which we also checked. And then, yeah, this is something already presented. And then as you change some parameter, you can go back and forth between Ising phase and then the toric code phase, and then higher central charge which is non-trivial on this side, is we transition to trivial phase on the torical phase. Okay, and then of course this we don't. If I make systems circumference larger and larger, this is going to be a sharp drop. This is the first numerics I want to share with you. Another example is the fractional quantum Hall systems. So I consider something you may have heard about. We consider Lafrance state. Well, we actually didn't take a Lafrance state, but we take a system which can realize something like a Lafrance wave function. It's a systems with lambda level, and we add some interactions. Okay. And then over years, DMRG techniques has been developed to study two-dimensional fractional quantum Hall effect. And then my collaborator Roger and my advisor, technical advisor Mike, they are kind of forefront of developing these algorithms. And then basically you can do DMRG as if it is like a one-dimensional system, although it is really a two-dimensional system. So we have an infinite cylinder, but you can consider matrix product state type wave functions in this direction. Okay. But anyway, we use this DMRG technique for the fractional quantum Hall states, and then once again we can compute the expectation value of partial rotation operator, and then as I make the circumference large enough, eventually the phase saturates to some interesting value like a 0.35 and so on and so forth. And then once again, we compare these results with the theory prediction, and then we basically check that they agree very well. Okay. We can also compute momentum polarization. Okay, so with this, I think I want to summarize and then outlook. So yeah, so basically we found a physical way or a very explicit way of extracting higher central charges by using partial rotation operators. So yeah, from our perspective, at least this is useful at least for numerics. But of course, we may be interested in doing this really in experimental systems or at least some quantum devices. Because, as I mentioned, a topological entanglement entropy has been already used in quantum computers. So yeah, being optimistic in the near future, maybe the type of operations, partial rotations we studied in this paper, it may be also studied in the quantum devices in the future. And then we can extract non-trivial information of many-body ground state, which may be very complicated in principle. Then, yeah, of course, another question is other interesting one, more creative way of extracting topological data by perhaps using other non-local operations and so on and so forth. Okay, so thank you for your attention.
Thank you for interesting talk. Now the session is open for question. Yeah, please. Please, it's microphone. Yeah, this one.
Yeah. So, can I ask? Is it possible to extract this with open boundary condition, like in a plane?
Yeah, that's actually a good. Short answer is yes. So actually, with my paper with Ken, where we didn't study fractional state, but we study SPT state, we actually took just a system on the plane, and then we picked up the disk region, and then we do the sum rotation. So that is also possible. Other possibility, maybe it's not for the DMRG, but we could also study just a finite cylinder, and then we could compute partial rotation operations. Historically, for the momentum polarization, people first study the finite cylinder. So it's doable.
So like for the disk case, is it like, say that you take like a square does it matter like the square has corners?
So yeah, so that's the so I think generically you want to be consistent with the discrete rotation symmetry of your underlying lattice. And the I mean, yeah, I think it may matter. Yeah, that may limit the n you can realize in the lattice.
Thank you.
Can this partial rotation be used for to extract the data for modular S matrix rather than the T matrix?
Yes, yes. Good. So, yeah, sorry. Maybe I didn't emphasize, but S will enter if I consider non-trivial ground state. So yeah, it will pick up some contribution from S. Yeah, I mean, I'm not entirely sure if I can isolate this, but it certainly pick up some information.
I see. And is there any obstacle to analytic continue to a non-integer n?
Yeah. So that is perhaps yeah. So that's for small rotation. Yes. So small rotation. It's sorry. Maybe this is not the right. So small rotation. It is just the momentum polarization. So you could do, theta, which is very close to 2 pi over n. And then that's a good question. Off the top of my head, I don't know the answer, but I think it's doable. Yeah.
Well, what is the risk? Why is it restricted to the integer n to prove this one?
Yeah. So there may be several things I could say here. So so yeah, from the perspective of operation itself, certainly we don't have to limit to these discrete rotations. But first of all, in the very definition of higher central charge, n has to be just integer. So we cannot. I don't know. There may be something interesting we could do as we change and analytically continue n into arbitrary real number. But here it's clearly integer. Then another geometrical insight I didn't say. Sorry, maybe I should say is that higher center charge can be understood as something which is associated to the length space partition function, which comes with integer n. So idea is that as you cut out the disk region of 2D space, you rotate and glue it back, you can effectively create a length space. So n is the integer n in the length space, which is discrete. Yeah, I'm not sure this is the satisfactory answer, but yeah, we consider just the discrete n.
The question? Yeah.
So n equals 0 case, you have a total quantum dimension, like quantity.
Right.
So that appears in a topological entanglement.
True.
Maybe this is related to some higher version of topological entanglement. This is very naive. I mean, theta A,
yeah.
I think twist. Right?
Yeah.
To anyone.
That's
So
right.
maybe add some twist to topological entanglement. Maybe.
Yeah, we can perhaps define higher version of total quantum dimension. Yes. good question. I mean, we could, for example, just compute something similar to symmetry resolution of entanglement. You do the symmetry operation partially on region A, and then you can do entanglement entropy calculation.
Maybe the symmetry, maybe rotation.
Yeah. In
something
this
like
case,
that.
symmetry is
can-
rotation. So yeah, I don't know the answer, but I would try symmetry resolution by rotation that may capture higher version of quantum dimensions, the total quantum dimension. Yeah, but yeah, still this is 2, right? So this is 2. We change n, but this is 2. So I think you may, I thought you may want to change power here, or yeah, I'm not sure what they could. Yeah, power of theta we can change. Yeah.
I have a question. So you showed the example of numerical calculation only with finite central charge and finite higher central charge. Higher. Yeah,
Yes.
Yeah. So do you have this example in which the chiral central charge is 0, but higher central charge is non-zero?
Yeah, so we actually working on it.
I see.
Currently, we are numerically sort of working, but we see some strange behaviors, and then I think generically we expect no reason for our method not to work, but just some details we are still working on it. So yeah, I mean, fair question, right? So because we want to have a non-trivial examples.
I see.
Yeah.
What is the physical meaning of higher central charge? So,
So there are many questions depending on what is the physical. So for example, so for example, you may be interested in something like a transport quantities, which may extract higher central charge. That may be physical meaning. For example, the regular central charge, we can use each transport to measure it. So that's a physical meaning. But we don't have such interpretation. But instead, we have we don't do transport. We do physically move particles. So that's the formula we have now. But yeah, good question. I think there may be more things we can do along that line by thinking about the physical meaning of higher central charges.
Thanks. All right.
Maybe I have a layman question, but why do they call higher central charges? Do they have any algebra behind it? I mean, in the case of usual central charge, you have lots of algebra. And then
so now you're asking math, I think.
Yes.
Motivation. So like I said, I think these people are interested in generalizing the formula for the chiral central charge in terms of modular data. And then they found some
so it's like
formula.
It's really a center of some algebra, or do they just go because it's a generalization of?
Yeah, good question. I can't really answer, but these are people interested in, I don't know why they call it higher. That's what you're asking, but but generalizing,
I understand
Gauss sum formula with new parameter integer n. Yeah.
Okay, thank you.
Question, comment? Question, comment in audience in Zoom? No? Okay, so then let's close the seminar. Let's thank speaker Shinsei again.
Thank you for your attention.